Okay, let's dive right into this. Welcome to today's Explainer. We're taking a really focused look at the massive wave of announcements that just dropped out of NVIDIA's National Robotics Week in April 2026. We are cutting straight through the hype to see what the actual ground-level state of physical AI looks like right now. We're going to look at what NVIDIA is building, the real-world hurdles of taking these systems out of the lab, and what it all actually means for you developers out there building this stuff.
I mean, it's the ultimate question, isn't it? Can a robot truly understand a natural language command and then reliably execute it in our messy, totally unpredictable physical world? In theory, sure, it sounds absolutely amazing. Just tell a machine what to do, and boom, it does it. But the reality of actually deploying these robots, it's incredibly complex. And that massive gap between the theoretical promise and the practical, everyday application, well, that's exactly what we're exploring today.
So here's our roadmap. We'll kick things off with the physical AI revolution and unpack NVIDIA's new tech stack. Then, we need a vital reality check on the lab-to-factory gap. After that, we'll look at the startups actually deploying this tech right now. And finally, wrap up with some concrete takeaways for AI developers. Let's get right into it.
All right, Section 1, the physical AI revolution.
We're witnessing a major shift here. NVIDIA isn't just launching one-off products anymore. They are aggressively building an entire ecosystem around physical AI. And the absolute headline announcement was NVIDIA Isaac GR00T. So what is it? It's an open development platform and a general-purpose foundation model. The really ambitious goal here is letting robots understand natural language and translate that directly into physical actions. Because historically, robot control has been incredibly brittle, right? It required this exhausting, task-specific, line-by-line programming. GR00T is aiming to completely shatter that old paradigm, drastically cutting down the need to manually code movements for every single new deployment.
Let's move to and see how this builds into our next part. Section 2, Unpacking NVIDIA's Tech Stack.
Now, what's super interesting here is how all these different layers seamlessly fit together to solve the core data problem in robotics. Right at the top, you've got Isaac GR00 handling the vision, language, and action reasoning. Sitting just beneath that is Cosmos. These are world models generating synthetic data to actually capture physical causality. Then, you factor in Newton 1.0, which is an open-source physics engine co-developed by Google DeepMind and Disney Research, and that ensures things like collisions and object contacts behave exactly like they do in the real world. Finally, the whole shebang comes together in Isaac Sim 6.0 for virtual testing. The big takeaway for us? Robots trained on Cosmos world models that fundamentally understand physics, they require a dramatically lower amount of real-world data to actually perform reliably.
To give you a concrete idea of what this stack actually looks like in action, just look at the NemoClaw integration. A developer can type a plain text instruction, something simple like move 2 meters forward, and NemoClaw automatically translates that directly into executable Python scripts right inside Isaac Sim. Literally zero manual coding required. I mean, this is a massive shift. It allows for incredibly safe testing and collaborative, language-driven robotics in a physically accurate virtual environment long before a physical robot ever even powers on.
Which brings us to Section 3, the lab-to-factory gap.
Okay, we need a crucial reality check right about now. Listen to this quote from Anthony Vetro, the CEO of Mitsubishi Electric Research Laboratories, or MERL. He points out that robots still struggle to generalize outside the data they are trained on. It's a pretty sobering reminder, honestly, because despite all these incredible advances in sensing and foundation models, human-level reliability in contact-rich manipulation tasks, we just haven't reached it yet. Humans can adapt instantly to sensory feedback, but robots, they are still heavily reliant on their training data.
Just look at the stark contrast between these two worlds. In a lab, everything is perfectly tuned and structured, but out on the factory floor, oh man, you've got variable lighting, you're dodging 20-year-old legacy equipment, and there are completely unpredictable humans walking around everywhere. When robots face this reality, their pre-programmed assumptions just break. And in this industry, if dropping a robot into an existing workflow doesn't bring rock-solid reliability from day one, it simply doesn't ship. The integration costs are just way too high for systems that only work in theory.
So how on earth do we fix this? Well, according to Vetro and the ongoing research at MERL, overcoming this gap boils down to a few key things. First up, predictive sensing. A robot absolutely needs to anticipate human and object movement before contact ever happens to ensure safe collaboration. Second, these models have to explicitly handle real-world uncertainty, not just optimize for some perfectly average case scenario. And third, this is big for the bottom line, to lower the massive costs of gathering training data,
operators are increasingly using augmented reality and audio-visual interfaces. So instead of manually coding everything, human operators are guiding robots through simulated or voice-annotated interactions. This completely changes the economics and the scalability of actually deploying robots out in the real world.
All right, let's dive into Section 4, Startups Deploying Real Robotics.
And this brilliantly illustrates that we aren't just talking about glossy research demos anymore. Look at these companies from the NVIDIA Inception cohort. You've got Burrow building autonomous ag robots for grape harvesting. Deltia is optimizing assembly lines with AI-driven manufacturing intelligence. Config Intelligence is laying down the data infrastructure required for complex bimanual, two-handed robots. And Happily Robotics is designing haptic control steering wheels. These are real, shipped products operating in high-stakes sectors like agriculture and manufacturing, where the tolerance for failure is literally absolute zero.
I want to focus specifically on Happily Robotics for a second, because this is absolutely vital. Contact-rich tasks, think intricate factory assembly or delicate crop harvesting, they require force feedback. Pure vision-based systems simply cannot provide the subtle tactile physical information needed for those kinds of tasks. If your application involves physical contact with the world, incorporating haptic control isn't some nice-to-have luxury. It is absolutely required.
Which brings us to our final part, Section 5. Takeaways for AI developers.
So the crucial point is really managing expectations around open models. Listen, Isaac GR00T is a foundation. It is not a finished, ready-to-deploy product right out of the box. Yes, having a general-purpose model raises the floor incredibly high so you don't have to build language grounding from scratch. But make no mistake, guys, these models still require some serious heavy lifting and heavy fine-tuning for your specific hardware and your unique task domains.
The second huge takeaway is the absolute necessity of sticking to the simulation pipeline. The workflow needs to look exactly like this. First, you generate synthetic data using Cosmos. Second, you test extensively, and I mean extensively, in simulation using Isaac Sim or Isaac Lab. Only then do you move to step 3, which is edge deployment on hardware like Jetson Orin or Thor. I really cannot stress this enough. Development teams who try to cheat and skip the simulation step, jumping straight to hardware iteration, they are going to face drastically higher costs and much slower iteration loops.
Which really leaves us with this final, incredibly provocative question to chew on. How quickly will that lab-to-factory gap actually close? We are already seeing structured environments, like agricultural automation, move incredibly fast. But the timeline for highly unstructured, totally unpredictable environments, that remains the ultimate test for the physical AI industry. The tools are here, the foundation models are open, but bridging that final gap to the physical world, well, that's going to be the defining challenge of this decade. Thank you so much for joining me for this explainer, and I really hope this gave you a much clearer, structured understanding of the real state of physical AI today.